Okay, hello everyone, welcome to the Graphics Programming Virtual Meetup. Today we will talk about the PBRT book and 10.4 image texture. So image textures store to the arrays of point sampled value of texture function. We can use this sample to reconstruct a continuous image function that can be evaluated at an arbitrary ST position. These sample values are often called texels, since they are similar to pixels in image but used in textures. And image textures are the most widely used type of textures, yes. Usually when we talk about textures, we talk about image textures rather than the procedural textures described in previous sections. Yeah, with textures, without textures, the difference is a lot. As with most of other type of texture, PBRT provides both a float and a spectral variants. So both implementation inherit from image texture base to provide some common functionality, but they will just present the implementation of spectrum and image texture because float image texture is analogous. So color of the spectral image textures constructor provides a texture mapping function. File name just various parameters, how boundary conditions are managed, and how colors are converted to spectral samples. Oh, yeah. Yeah, I think just there's this article very recently talking about the same issue. Basically, you have image in sRGB and you want to use in a spectral renderer. What to do? Basically, put the link in here. So RGB colors are transformed into spectra differently depending on whether or not they represent reflectances. So spectrum type records what type of RGB a texture represent. And content of the image file are used to create an instance of the mipmap class, store the text in memory, and handle detailed reconstructing and filtering to reduce aliasing. So okay. So it's a get mipmap from cache, otherwise create a mipmap. And the floating point scale can be specified with each texture. It's applied to the evaluate function. Invert will cause the texture value to be subtracted by 1. While the same functionality can be achieved with scale and mix texture, it's easier to also provide the functionality directly in the texture here, which is more efficient rather than and also on the GPU. Yeah, I guess the indirection is definitely not efficient on GPU or on CPU, but much less efficient on GPU. Each MIP map may require a meaningful amount of memory, and complexing may have thousands of image textures. Because on-disk image may be reused for multiple textures. You see, PBRT maintains the table of MIP-maps that have been loaded so far, so they are only loaded into memory once, even if they are used in more than one image texture. Yeah. PBRT load texture in parallel after the scene description has been parsed. Doing so reduces startup time before rendering begins. And mutex is used to ensure one thread access to texture cache at a time. Now I guess the texture cache is changed during rendering. Otherwise, I can think of a solution that you only need the mutex during the startup and then during loading textures, and then you just don't change. But I guess during rendering they may load new texture, something like that. Not sure. But anyway, they have mutex to protect the access to the texture cache. Sorry, Mike, are you trying to say something? It's really quiet.
No, sorry. I just forgot to mute.
Sorry, I guess I have some background noise at here too, but yeah, anyway. Sorry, wait a minute. 小云，你能把门关一下吗？ Anyway, sorry. This texture info as a key to map. It's a pretty large structure. Okay, they do comparison. And if a texture had not yet been loaded, a call to create from file yields a MIP map for it. If the file is not found or an error reading, the PBRT exits with an error message. So a null pointer return value does not need to be handled here. Okay, so PBRT does not just return some dummy texture like some real-time renderers do, but instead they just exit. Yeah, I guess it's a reasonable decision since it's an offline render. Anyway. Before describing the MIP map implementation, we will discuss the evaluate method. So evaluate method takes the eval context and the wavelengths, apply texture mapping, loop up filtered RGB value in MIP map, and So it's easy to compute the ST texture coordinate and their derivatives for filtering with the texture mappings to the map method. However, the t coordinates must be flipped because image and MIP map defines 0, 0 to be the upper left corner of the image, while image texture has 0, 0 at the lower left. Okay. And the filter method provides the filter value for the image texture over the specific region. Any specified scale or inversion is easily applied to the value it returns. A call to clamp 0. To ensure no negative value is returned, and an RGB color space is necessary in order to interpret the meaning of RGB color value. Yes, which people often ignored in real time. Anyway, normally the code that read image file from disk returns a RGB color space with the read image. Most RGB image formats default to sRGB. Yeah, but some allow specifying an alternative color space. Color space and value of spectrum type make it possible to create an appropriate type RGB spectrum, and in turn its sample can be called to get the same sampled spectrum that will be returned. If MIPMap has no associated color space, image is assumed to have the same value in all channels, and a constant value is returned for all the spectrum samples. Verified by dtrack. Okay, and for MIP maps, I guess this is the interesting part of this chapter. So if an image texture function has a higher frequency detail, then can be represented by the texture sample rate. Aliasing will be presented in the final image. Because there's a motivation for MIP maps, and any frequency higher than the Nyquist limit must be removed by pre-filtering before the function is evaluated. So 10.5 shows the basic problem we face. The image textures has textile that are sampled of some image function at a fixed frequency. The filter region for the lookup is given by its ST center point and offset to be estimated texture coordinate location for the adjacent image samples. These offsets are all estimates of the texture sample rate. We must remove any frequency higher than twice the distance to the adjacent samples in order to satisfy the Nyquist. I don't know how to pronounce that, sorry.
Criterion? It's like criteria, but with an eon.
Yeah.
Silly word.
Yeah. Yeah. yeah, I guess one thing as a like non-native speaker is that I have no intuition of how to pronounce words I don't know. So sometimes I will just pronounce things incorrectly or just just don't know how to pronounce it. Anyway, let's look at this image. Give a point at which perform an image map lookup, which is solid point to the center, and estimate the texture sample rate denoted by the adjacent solid point. It may be necessary to filter the contribution of a large number of texels. Yeah. Texture sampling and reconstruction process has a few key differences from the image sampling process discussed in Chapter 8. I forgot what Chapter 8 talked about. It's mostly theories, I guess. No, but I guess this image is a really good demonstration of the aliasing problem. This difference makes it possible to address a problem with more efficient and less computational expensive techniques. It's inexpensive to get the value of the sample. Yeah, only an array lookup is necessary. Because the texture image function is fully defined by a set of samples, there is no mystery about what its highest frequency could be. There is no uncertainty related to the function behavior between samples. This difference makes it possible to remove details from texture before sampling by pre-computed mipmap, basically. The texture sampling rate will typically change from pixel to pixel. So the sampling rate is determined by the scene geometry and its orientation. And the textual coordinates mapping function and the camera projection and the image sample rate, just a lot of stuff. Because the textual sampling rate is not fixed, textual filtering algorithm need to be able to filter over arbitrary region of texture samples efficiently. So MIPMAP class implements a number of methods to texture filtering with spatially varying filtering width. Can be found in utils MIPMAP. The filtering algorithm offers a range from simple point sampling to bilinear interpolation and trilinear interpolation. Fast, easy to implement, and was widely used for texture filtering in early graphics hardware. To elliptically weighted averaging, which is complex but return extremely high quality result. So this 10.6 compare the result of texture filtering using the trilinear interpolation and the EWA. Now that's a lot. Very different result. Both gives a much better result compared to 10.8, 10.1. Oh yeah. But trilinear is not as effective as EWA at handling strongly anisotropic filtering footprint. Yeah, because it's filters a like box region, I guess. Which is why the lines on the left sphere are blurrier. In regions with highly anisotropic filter footprints, such as the pole of the sphere and toward the edge, EWA resolves much more details. So if an RGB image is provided to the MIPMAP constructor, its channel should be stored in RGB order in memory. I'm not sure why this matters, but anyway. So it takes the image and then generates a pyramid. To limit the potential number of texels that need to be accessed, this filtering method uses an image pyramid of increasingly lower resolution pre-filtered version of the original image to accelerate their operation. I guess everyone here at least have an idea of how this kind of stuff works, right? So if you don't, then please ask. Anyway, so original image texels are at the bottom level of the pyramid, and yeah, image at each level is half the resolution of the previous level, etc. And the top level is a single texel representing the average of all the texels of the original image. And the pyramid needs at most 1/3 more memory than storing the most detailed level alone, and it can be used to quickly find the filtered value of a large region of the original image. Yeah, if a large area of text need to be filtered, a reasonable approximation is to use a higher level of pyramid. So pyramid is just a vector of image. There's their own class of vector. Does that mean they put this as is to the GPU rather than use GPU native? I guess that will not be the topic today. Or maybe they just want to use their own vector because they like it better than STL, whatever. Choice of filtering method and parameter used by EWA method are represented by MIPMAP filtering options. So filtering function can be point, bilinear, trilinear, and EWA. It's just getters and giving an image pyramid, we define some utility mipmap method and retrieve the text value at a specific level. And the discrete integer pixel coordinate. For the RGB variant, there is an explicit assumption that the image channels are laid out in the RGB and maybe A order. Oh, because their image is generic. I understand it now. The image is generic, so it can be any kind of channel laid out, so they just make this assumption, I guess. So filter function returns a filtered image function value at the position of ST. Takes two derivatives. So EWA filtering technique to be described shortly use ST to compute an anisotropic filter filtered by different amount in different dimensions. The other three use an isotropic filter that filter both equally. So isotropic filters are more efficient than anisotropic filter, though they do not give the same result. Yeah, for them only a single value is need to specify the width of the filter. The width is conservatively choosing to avoid aliasing in both the ST direction. So it's just 2x max of the direction, each components of the differentials. Yeah, this choice means the texture viewed at an oblique angle may appear blurry. Yeah, because the required sampling rate in one direction can be very different from sampling rate along the others in this case. So filtering over many texels for wide filter widths can be inefficient. This method chooses a mipmap level from the pyramid, such that the filter region at that level would cover 4 texels at that level. So okay, so mipmap choose a level that covers 4 pixels. So if we choose this level, basically 4 texels. The resolution of levels of the pyramid are all power of 2. The resolution of a level L is this, and to find the level with a texel spacing with W requires solving this. Yeah, for L. In general, yeah, this will be a floating point value. Value of L greater than the number of pyramid level correspond to a filter width wider than the image, in which case the single pixel at the top level is returned. Yeah, if the level is too large, then it just returns the top level. And they also compute an integer level by doing floor. Interesting. Why they don't use round? I don't know. Oh, I guess they want a lower level, and then when doing trilinear filtering, they just always like filter between those two levels, I guess. So for point sample texture lookup, it's only necessary to convert the continuous texture coordinates over 0 to 1 to discrete coordinates over image resolution and retrieve the appropriate texel value via the texel method. Yeah, for the point sample, it's just really simple. We get a resolution. And bilinear filtering, which is equivalent filtering using the triangle filter, just use a bilerp. And yeah. So they do bilinear filtering separately for each channel. So apply triangle filter to the 4 texels around the sample point will either filter over too small a region or too large of a region. Yeah, so the trilinear filter option apply the triangle filter at both of these levels, yep, and blend them together by additional lerp. By applying a triangle filter to 4 pure texels at 2 levels in this manner does not generally give exactly the same result as applying triangle filter to the original pixel. The difference is not too bad in practice, and the efficiency of this approach is worth its penalty. And in any case, elliptically weighted average filtering approach should be used when the texture quality is important. And EWA algorithm fit ellipse to the two differential vectors in the texture space and then filter the texture with a Gaussian filter function. It's widely regarded as one of the best texture filtering algorithms in graphics, as be carefully derived from the basic principle of sampling theory. So unlike the triangle filter, it can filter over an arbitrarily oriented region of texture. Different filter extend in different directions. And also it's anisotropic, since it can adapt to a different sampling rate along the two image axes. We will not show the full derivation of this filter here, which I'm glad, because I will not be able to understand that. Anyway, on the way to note that it is distinguished by being a unified resampling filter. Because it simultaneously computes the result of a Gaussian filtered texture function convolved with a Gaussian reconstruction filter in image space. This is in contrast to many other texture filtering methods that ignore the effect of image space filtering or equivalent, assume it is a box. Yes, even if Gaussian is not being used for filtering the samples for image being rendered, taking some account of the spatial variation of the image filtering improves the result. Assuming that the filter being used is somewhat similar to the shape of Gaussian, as some other like sync filters are. So the partial derivative of the texture quantity defines the ellipse. The lookup methods start by determining which of two axes is longer than the two, swapping them if necessary, and the length of the shorter vector will be used to select a map level. If the ratio of the length of the longer vector to the length of the shorter one is considered, large ratio indicates a very long and skinny ellipse. Because this method filters texture from a map level chosen based on the length of the shorter differential vector. Large ratio means a large number of textures need to be filtered. To avoid this expense and also ensure any EWA lookup takes a bounded amount of time, the length of the shorter vector may be increased to limit this ratio. The result may be an increase in blurring, though usually not noticeable. So they have an option. Basically, if the ratio is too large based on this option, then they rescale. And like the triangle filter, EWA filter use the image pyramid to reduce the number of texels being filtered for a particular textual lookup, and choosing a map level based on the length of the shorter vector. Given the limited ratio of the clamping above, the total number of texels used is thus bounded. And given the length of the shorter vector, the computation to find the appropriate pyramid level is the same as was used for the triangle filter. Similarly, the implementation here blend between the filter result at the two level around the LD, just like a trilinear. So again, they lerp between two levels and call EWA at each level. And for each EWA call, again, if the level is too large, we just returns the top, basically. So this method first convert from textual coordinate in 0 to 1 to coordinates and differential in terms of the resolution of choosing a MIP level. Also subtract 0.5 from continuous position coordinate to align the sample point with the discrete textual coordinate. Next, compute the coefficient of implicit equation for the ellipse centered at origin that is defined by the vectors placing the ellipse at the origin rather than at ST simplify the implicit equation, and the computation of its coefficient can be easily corrected when the equation is evaluated later. So form of implicit equation for a point ST inside such an ellipse is like this, and more computationally efficient to divide by f. And they will not derive it and also not talk about what those ABC means, but anyway, it's here. So we have something to check whether a point is inside the ellipse, and then to find the ABB in discrete integer textual coordinate. For texels that are potentially inside the ellipse. and then loop over all those candidate texels, filtering the contribution of these that are in fact inside the ellipse. And the bounding box is found by determining the minimum and maximum value that the ellipse takes in the ST direction. These extrema can be calculated by finding the partial derivatives, finding their solution for s equal to 0 and t equal to 0, and add the offset to the ellipse center. Anyway, the bounding box. And the bounding box is shown, then EW algorithm just loop over the texels, transform each one into the coordinate system where the texture lookup function is at the origin with translation. Then evaluate the ellipse equation to see if the texture is inside the ellipse. And compute the filter weight of texture if so. The final filter value returned is a weighted sum over texels inside the ellipse, where f is the Gaussian filter function. Also sum of weight. Just do nested loop. A nice feature of implicit equation is that its value at a particular texel is squared ratio of the distance from the center of ellipse to the texel to the distance from the center of ellipse to the ellipse boundary along the line through that texel. I need to read this again. This is very long sentence. Its value at a particular texel is the squared ratio of the distance from the center of ellipse to the texel to the distance from the center. The distance from the center of ellipse to the ellipse boundary along the line through that. Sorry, I gave up. Anyone understand what that means? This sentence? Okay. This value can be used to index into a pre-computed lookup table of Gaussian filter function value. And so anyway, the lookup table is pre-computed and available as a constant array. So this, similar to the Gaussian filter using image reconstruction, the filter function is offset so that it goes to 0 at the end of its extent rather than having an abrupt step. Okay. So this is this chapter which talks about map and trilinear filtering and the EWA, which I still need to wrap my head around. So I guess I get the gist, but probably not the Gaussian filtering part, but I get the gist of how it filters the ellipse basically, and rather than a square. Any comments before we end the recording? Okay,